So yeah, I decided to try to change the setup. We'll see how this goes because the camera quality is not ideal. So hopefully this will be more useful. So I know it's kind of late. Yeah, but at least it's something. So we can just jump into today's first theorem. Remember last time we discussed this notion of something you should know, this notion of supremum, which is like the lowest or the smallest upper bound for a set. And the main idea, so the thing was we were trying to prove like the real line is connected, right? So why do we even care about that? We wanted to show the reals are connected. So suppose you have like the reals are u and then some v. That should give you the entire thing. And we said, well, the problem should be here with the supremum of some part here. Right. So that today we need to formalize that idea somehow. So theorem, we know how to prove this. Theorem 1 for today is any open interval of the form a comma b inside of the real line is connected. So we'll spend like probably 25 minutes trying to prove this, which is absolutely obvious, by the way, at least when you look at the picture. So this is telling you pictures are something and then proofs are something else. So let's prove this. The proof will be essentially this picture, but yeah, we need to do stuff. So how do we operate here? We assume it's not connected, fix a separation, and go from there. So assume for contradiction that AB is not connected. So that means we have a separation. AB equals U union V is a separation. So that means we have U open in AB, V open in AB, they intersect trivially, and they are both non-empty. So what we're going to do here is we have two non-empty sets, U and V are non-empty. We'll just fix some point small u in U and some point small v in V. So what I'm doing here is here we'll have a very important picture for this proof. Here's my AB, B, A, there is U doing something, U open, then we have V. Of course, this is nonsense because we don't know if U and V are like intervals, but we know they are unions of intervals, right? And they do not overlap. Then maybe you will have some other piece here. Who knows? And there we don't really know what's going on. We could have some V here or not. Who knows? But the thing is, only one of these overlaps will be enough to land a contradiction. So we have points in U, a point in U, a point in V, and we can just assume U is smaller than V. Otherwise, switch U and V. So which are different, So U is not V because sets are disjoint. So assume without loss of generality that U is the one that's smaller than V. So how do we write this portion of U? The picture is clear. How do we write that? Well, now let me just assume here's my little U. So maybe I want to move these guys up. Here's my little u. Here's my little v. And we are sure that the problem should be here. That should be the problematic point. So how do we write this portion here? How do we write this portion? Well, that's tricky. But if you remember the intermediate value theorem proof, so this set is kind of weird, but not really. So S is going to be points in the interval such that an entire chunk from U to that point, S, but here I will keep it open, is inside of U. Right, so I'm taking all points here because that means this entire chunk is inside of U. I cannot take a point here because then you have this thing in between. So that's how I'm choosing to write those guys. So things to note. First, S is non-empty. Why is that? Why is S non-empty? Contains U. Contains the singleton U. So it contains the closed interval from U to U. That's why I want to keep this guy closed here. Because U, little u, lives in S. This is little u. And the other one, so I want to take the supremum, so I need to say it's a non-empty bounded set. S has an upper bound. And that's because my S is a subset of AB. So B is an upper bound for every element in S. Okay. And now, crucial part. Let's take the supremum. S0 to be the supremum of this set S. That's this guy here. That's our S naught. So the proof will now go into several steps or claims. So this exists because 1 and 2. And now a bunch of claims. Claim 1. So this one is kind of nonsense. You will see why it's useful later on. If we take any any point x in V, which is smaller than U, sorry, bigger than U, then it's going to be an upper bound. Then X is an upper bound for S, for the set S. So let's prove this claim. Why is this true? So we want to show X is smaller than or equal to every element in S, right? That's what we want to show. So suppose this is not true. So for a contradiction, this is not true. Then if x is not an upper bound, then there needs to be, there is some point. How do I call this point? Let's call it S, which is, if we're saying x is not an upper bound, S needs to be smaller, sorry, S needs to be bigger than X for some S in S. S bigger than X. That's what it means for X to not be an upper bound. There's something inside that's bigger than it. Okay. And then what do we do with this S? What can we do with this S? So remember, S is kind of here, but X lives in V. Do you see the problem with that? Our X lives between U and S, right? Right. We lives in S, so X lives in U S, which is inside of closed U S, which we are assuming is inside of U, and this is because little s lives in big S. So that's not possible. So this is a contradiction, and this proves claim 1. So this proves claim 1. Because we're saying X lives in U, but it was supposed to live in V. Okay? So when I make a write-out, contradicts U intersection V is 70. Okay, that was claim 1. Why is this useful? You will see. Claim 2. So the thing with this S naught, we prove it cannot live in U, and it cannot live in V. Then it's nonsense because U union V is everything. Well, not really everything, it's AB. So we need to prove that S naught lives in AB. Should be absolutely obvious, but we need to prove it. In principle, the supremum lives in the reals. We need to prove it's there. So how do we prove this? Let's prove first, for example, A smaller than S naught. And then we'll prove B is bigger than S naught. So why is this true? It's kind of easy. Since U lives in S, we have U smaller than or equal to S naught, because S naught is an upper bound, right, of S. But A is smaller than U, and this is because U lives in AB. So this is because S not upper bound for S. And then we're pretty much done. Maybe hence A is smaller than U, smaller than or equal to S naught. That gives A smaller than S naught. So the steps are not complicated, but a bunch of them. So now let's prove S naught smaller than B. So the idea here should be similar. Now we have, what do we have now? we have a point V in V. So we have a point in V. I'm trying to use claim 1. And we know that U is smaller than V, because that's how we started. We know that V is an upper bound. That V is an upper bound for S. And this is claim 1. So you can already see how we're using it. I'm going to use it at least 3 times. This is the first one. And then we're done, right? If V is an upper bound, it needs to be bigger than or equal to S naught, because S naught is the smallest one. But now V is smaller than V. It's in AB, so V is smaller than V. So very easy steps, not so easy how to apply them. What's the correct order here? Hence, it's not smaller than B. And that's the proof for claim 2. Okay, claim 1, claim 2, very smooth. So I don't really want to prove this, but you will see why I need this. So this is claim 3 minus epsilon, because it's something that we need for claim 3. Claim 3 minus epsilon is that this closed interval, well, not really closed, open here, I guess, yeah, is inside of U. Makes absolute sense if you look at the picture. So how do we prove this is true? Same as always, assume it's none. So assume, so this is the proof for this claim. Assume not true. If it's not true, then there is some point X that lives in U. It's not intersection V. And it cannot be U, because V and set U are disjoint. We also have X different from U. So this X is bigger than U because it lives here, but it's not U. And X lives in V. This means that X is an upper bound for S. And that's claim 1 again. So this is claim 1. And that's problematic because X is smaller than S naught. This contradicts that X is smaller, strictly smaller than S naught, which is the smallest upper bound. So this proves this claim. Are we okay? Claim 3. Maybe I'll need more space for this. Let's start here. Claim 3. What I want to prove now is that this S naught, maybe let's use colors, S naught cannot live in U. And then claim 4 would be S naught cannot live in V. And that will be the contradiction. Lives in A, sorry, lives in AB, in the interval, which is U union V, but it's not an element in U, it's not an element in V. So let's prove this. Assume again, for a contradiction, that S naught lives in U. Funny fact, I never used that U is open, which is weird. So let's use it now. Since U is open, there needs to exist some positive epsilon such that not only S naught, but this open ball or open interval lives inside of U. So what this is telling me is something like, here's my S naught. This is telling me, supposedly here we have V. This is supposed to be V already. Here we have U. Of course, we don't know that anything bigger than S naught lives in V. We don't know that. So what can I do? Why would that be good? But how do we know that's an upper bound? Maybe we want to go this way. S naught minus epsilon over 2. So what's the problem with this? I need to cook up an element in my set S. And that's what we're not able to do so far. And this is the guy that should live in S. This guy should live in S. Is that right? Oh, no. Right, no. That's, of course, going to live in S. That's not a problem. The contradiction will come by showing that this guy lives in S. Sorry. So the contradiction will come by showing that this guy lives in S, which is bigger than one upper bound. So it's already wrong. Why would this guy live in S? We need to show that if you close it here and go all the way down to U, which is somewhere over here, then the entire set is inside of U. Why is that true? Well, this little portion here, this lives in U. That's what we're saying here. And now we can use this claim over here. We also know this guy lives in U. So everything here lives in U. This is the other part of the claim. So by claim 3 minus epsilon, we know that U S naught is inside, S naught open, sorry, is inside our U. So if we do it closed here, S0 minus epsilon over 2, that's going to be inside of U. As a consequence, this entire U to S0 plus epsilon over 2 is going to be inside, closed here, inside of U. Right? So first statement is this guy. Second statement is this guy. And that's already a problem. Right? Because this guy is larger than one upper bound. So this means S0 plus epsilon over 2 lives in S, but it's larger than S naught. So this is a contradiction. You cannot have an element that's larger than any upper bound. And we even have the supremum here. Is that okay? So claim 4 will be S naught cannot live in V. And let me move this. Okay, claim 4. S naught does not live in V. So what's the point here? Yeah, this one is even easier. So let's just write through it. So assume it's the case, again, for a contradiction, S naught lives in V. Now use this open. We have some positive epsilon. Let me use epsilon 1 because I'll have two of those, such that the entire S naught minus epsilon, S naught plus epsilon 1 is inside of V. Here I'm using this open. Now, we also have we also know, I also want to distinguish this guy from U. Right? U is smaller than S naught. That means that for some epsilon, my U is going to be smaller than S naught minus epsilon 2. So what I'm trying to cook up here is something like this. Here's my S naught. And I want to distinguish it from U. But I also want this distance to be such that I have the entire V here. So if we take the minimum between these two guys, epsilon 1, epsilon 2, we'll have both. So we'll have S naught minus epsilon, S naught plus epsilon inside of P, and U is smaller than S naught minus epsilon. So what's the problem with this? Problem should come from claim 1. I want to have something inside of V that's larger than U. So it will be an upper bound. But this guy is smaller than the supremum, which that's not possible. So the only thing that I'm missing is maybe this guy does not live in V because I'm taking this open interval, right? But if I do this, this guy will live here. Right? So this is what I'm doing. This is my S0 minus epsilon over 2. Lives in V and is larger than U. And that's problematic. So again, this guy, S0 minus epsilon over 2, is an upper bound. For S, I claim 1 again. And this is contradiction, because S is not is the smallest one. So contradiction. And that's the end of plane 4. And that's also the end of the proof. So let's write that, but it should be clear now. So to finish the proof. So remember, we were going by contradiction. So we needed to learn the contradiction. The contradiction is that this guy S naught lives in A, B, which is U union V, but S naught is not an element in U, and it's not an element in V. So that's the contradiction. Okay. How long did that take? Oh, 35 minutes. That was a lot. How do we feel about this proof? So it's a complicated proof, but only because you need to like separate stuff all the time. And I do feel it's easier than the intermediate value theorem proof you use on your analysis class, because there is no function involved here. So maybe go back to, if you feel bad about this, go back to your analysis class, analysis proof, and you'll see, well, you were smarter before. This is easier than that. Now, second theorem. Well, maybe, yeah, maybe before I write this. So of course, I'm not going to give any applications of this theorem because it's like intervals are connected. We know that. We're just proving that. But I want to say something else. The thing I want to say is that the reals, the space of real numbers is connected. And also are the sets, the intervals. We have a bunch of these intervals. So all flavors, A, B, open at B, close at A, other way around, semi-infinite, A infinite, close at A infinite, negative infinite A, and now closed. Am I missing something? Yeah, the closed one. All these guys are connected. So are these intervals. So the proof here, this is corollary of the previous theorem. We know, we said this a while ago, all open guys here, they're all homeomorphic. We know that all these guys, the reals, anything like negative infinite A, open, A, infinite, all the open guys are homeomorphic to AB, open. So for example, you can go from AB to maybe negative pi half, positive pi half, like rescaling with a linear function. And then you can go from there to the entire reals with the inverse of the tangent function. So we know these things are true. And for this, for example, you can take logarithm. So we know all these things are true. So these are connected by the previous theorem. And for all the others, the only thing that we're doing is we're adding some cluster points, some limit points to some of these sets. So for the others, just use that if you have something connected, and you add some limit points, so that means something between A and its closure, then B is connected. This we proved last time. Okay, so these are the first interesting examples of connected spaces that we have. Weirdly enough, these are the first examples. Any questions about that? So this theorem is very useful. Because it tends to be easier to prove that things with no limit points are open, because you don't need to do weird things. So to freshen this up, we're going to discuss a theorem that you already know, probably. And the proof is very easy. I could have given this proof before the thing that I just did, but sometimes it's better to have all good news or bad news to begin with. So now we only have good news. This is intermediate value theorem. The intermediate value theorem. Well, that proof, I think it's bad news. Yeah. And good news is we have fancy theorems with intermediate value theorem. We have a fancy theorem with a decent proof. Could even say it's easy. Oh, yeah, thank you. Okay. So this theorem is going to start with a continuous function from some space to the real numbers where x is connected. But this should be a continuous function. Sorry about the English here. So I should say that f be a continuous function where x is connected. So this needs to be here. Then let's take 2 points, A and B, in X with, let's say, f of A is smaller than f of B. So we're just assuming we have 2 points with different values under F. And I can say smaller than because the function lands in the reals. Then the claim here is that for any value in between, or any R in between, there needs to be hit by some element in the domain. There exists some C in X with f of C equals R. And the picture is something like, here's your real line. Here's your F. Here's your X. That's connected. So if you hit 2 guys, then you hit everything in between. So the proof for this, we're going to go by a contradiction. Assume we have that this R is not in f of x. So that's what always mean by this. F of C equals R means R is in the image of F. So what I'm going to do in that case, or I shouldn't bound this is the real line. So what I'm going to do here is suppose there's something R here that's not hit by your function f, then I can just take whatever part of f of x lives there and whatever part lives here, and then take preimages. So here we have a separation of reals minus r, kind of separation of fx minus r, compute the preimage, and I will get two separate pieces here. So preimage will give you two separate pieces here. So how do we write this? We'll just show that f of x, we can write it as whatever portion of it intersects the positive part there, r to infinite, and then union, whatever part goes down. Okay? And this is because this guy r, so with this interval and this interval, I will form everything but this point. But that point is not in f of x, so I know this is true. Okay? And this is a separation. And everything is kind of direct here. These two guys intersect trivially because these smaller pieces intersect trivially. You're assuming f of a lives here, f of b lives here. Both are open because open intersection f of x. That's open with the induced topology. Open intersection f of x. So we're done. Maybe we can say something very easy. F of a lives here, so that guy is not empty. No, that should be f of b is the one that's smaller than this guy. So f of b lives here, f of a lives here. That means these two guys are not empty. They intersect trivially because these guys intersect trivially. And both guys are open. So open in R, open in R, intersection with f of x give you open in f of x. And that's all we need to do. So gives a separation of f of x, and this is a contradiction because x is connected and f is continuous. So f of x needs to be connected. We proved that last time. Okay. So that's an easy short proof. So I can also mention at this point very briefly what's important about the reals here. Not that much. Mostly that we have an order with some nice properties. And then the topology comes from that order. So there's this entire section in Bankers dealing with those things. And then this theorem, you can also replace x by such things. So if you're curious about those, you can go there. But the reason why I'm not going that way, and this might be because I'm not a topologist, but I don't know of many examples where, I don't know of many examples that come like this that are as important as the reals, not even close to that. There might be some nice examples. There are even some examples in the textbook, but I don't feel they are as important as the reals. So it's for me better to like have this particular case, knowing that everything could be generalized very easily. Okay. Path-connectedness. And this is probably what comes to mind when you think about connected spaces. So let me just write the definition because I'm sure you'll find it natural. So what's a connected space? Forget about the definition. What's a connected space? Yeah, please pretend you don't know the definition. What's a connected space? Anywhere from where? Absolutely. That's what you should have in mind. Given 2 points, you can travel. But if there is a hole here, well, you need to avoid it. That's probably what comes to mind when you think about connected spaces. But this is called path-connectedness. And why? Because we're saying there is a path. So definition. Let's take a topological space. The first thing I want to define is if you take 2 points, x and y in x, a path from little x to y in the space x is what do you think? What's a path? I want to define what's a path. What's this guy? What's this thing? It's a set, yeah. But what's the important thing about it? What's this set of points? Or what's important about this set of points? But what else? Something very particular. What you think is you start at x and you know how to travel to y inside your space x. It's a function going from an interval to x, starting at x, finishing at y. So it's a continuous map. Continuous map, always denoted gamma. If you need to know more than one path, you are in trouble because we always use gamma for these guys. From the closed interval 0, 1 to x. I'm using 0, 1. You could use AB or whatever you want, which will hit x at 0 and y at 1. And of course, what you visualize here is the image of gamma. 2, we say that x is connected, sorry, path connected. So I'm defining what's a path-connected space. Well, when is that the case? Right. If for any 2 points, x, y, there is a path on set x from x to y. So we'll see examples next time. Probably, yeah, I don't think we're going to be able to do that today, but let's finish with this theorem. This should be weaker or stronger than usual connectedness. How do you feel about that? Is it weaker? Is it stronger? It's stronger, right? If space x is path connected, then x is connected. So let's write a proof for this. I'm not going to go with a contrapositive. I'm actually going to use a contradiction. So assume X is path connected, but not connected. So whenever you prove an implication by contradiction, you assume P and not Q. That's what I'm doing here. And I really need both. So let's take a separation, which we know exists because X is not connected. That means U and V are open, trivial intersection, both of them non-empty. And let's take some X in U, Y in V. So what I'm doing is your X looks something like, here's your U, here's your V. Together, they give you the entire space. They do not intersect. I'm taking a point here. I'm taking a point there. There's supposedly there is a path, and that should be the problem. So take a path, gamma from 0, 1 to X, from U to V. And then what we're going to do, we can just pull back with gamma to 0, 1. We're going to have troubles here. So here's 0, here's 1, or the other way around, who knows? If you do reimage, how to raise this? Now, the thing is, the pre-images of U and V under gamma will give us a separation of the closed interval 0, 1, which is connected because we spent 35 minutes proving that. And that'll be a contradiction.
Would it also be possible to use the inequality plan?
Huh.
Like C comes around one, such that the image of C can't be in the
Let me think about that after I read this, but probably. So then when you do 0, 1, I'm just proving you have a separation. This is going to be the pre-image under gamma of your X, which is U union V. Pre-images are very nice with unions and everything else. Both are open because gamma is continuous. Both open because gamma is continuous. By the way, if you don't ask your path to be continuous, then this is nonsense because you can justify gamma of t to be x for every t different from 1, and then gamma of 1 to be y. It's very important that it's continuous. Otherwise, everything is path connected. So both open. The intersection of these two guys, again, pre-images are very nice, very well behaved. This is pre-image of empty, which is empty. And they are both not empty because 0 lives in pre-image of U because little u lives in U, and gamma of 0 is U, little u, and 1 lives in gamma inverse of B. That means we have a separation. So 0, 1 expressed like this, pre-image of U union pre-image of V is a separation of a connected space, which contradicts that the space is connected. And that's the end of the proof. So very briefly, what we'll do next time to begin with, if we're claiming the theorem to be true only in one direction, we'll need to understand the other direction. And the favorite example here is inside R2, consider kind of sine of 1/t, the graph of that guy, which is doing something crazy like this, and then it's kind of a usual sign. And then at this point here. There's no way for you to travel from 0 to any point in this path. But this guy is connected because this guy is a limit point of the graph. So we'll discuss that next time. Let me stop the recording.